Right, well, we've had 2 days of sunshine. We're getting to the last part of the day. The charge meter's just gone out. It just popped out, but well, we're certainly a lot higher than we were yesterday. Well, that's the voltage reading without the sun. Oh, it's coming on again. There we go. The sun's up and down at the moment. Oh, it's gone out again. Sun's gone down again. It sometimes goes like this. It starts flickering. It comes on, goes out because of clouds. And yes, we're doing quite well. Actually, let me show you the reset, because I don't know if it's going to work, because it didn't work properly because we were being charged yesterday. I'm just going to try pressing the reset button again at the back. Let's see. Actually, what I'll do is I'll pull the lead out, pull both the charge leads out. Right, so it's gone out. Reset. No, it doesn't want to do. It's got plenty of power, you see. Right, I'll plug these back in. Right, there we go, charging again. Right, well, we're doing alright. As I say, when there's plenty of power in my battery, it doesn't cut out, because I use the reset. The priority with these lithium-ion batteries is to prolong the life of the battery, so I've designed it orientated around preservation rather than usage, because once these batteries, not many people know this, but once you discharge lithium-ion batteries too much, below a certain point, they disable themselves and they're useless. And the last thing I want is a useless battery box. So I, at all times, I make it it's essential that the batteries are never discharged more than below about 80% or 70%, so that there's enough power in there to run the circuit, the cutout and recovery circuit. So, because that particular circuit only uses about 3.5 milliamps, which is very small, so that can run for several weeks, probably months actually, maintaining the cutout circuit even if there's no sunshine whatsoever. So anyway, there we go. It's going back up to 150 milliamps, because we're actually about at the time at the moment is 16:06. So according to my computer clock, so it's the last part of the afternoon now. I've had about an amp or so early today. The sun's actually quite high in the sky though now, but I've had my inverter on earlier on today as well, and the main battery's doing well, and I reset it earlier, so it's only been running for 5.5 hours since I last reset it, and I was testing it earlier. The reset circuit works really well, and I just thought I'd do a little bit of a add-on. But there was something else I was going to show you and I've forgotten what it was now. Let me just pause a minute, see if I can remember now. Pause, where is the pause? Oh, there isn't a pause on here. I've just got to stop and start again. Hang on. Right, I'm doing the update 11B, or you can call it update 11. But this is my schematic for the circuit. I originally got this schematic off the internet, but I made a lot of modifications. I changed the integrated circuit, the transistors, the MOSFETs, and simply because, let me just zoom in, because I customized it to do. I'm using Design Spec PCB, which is for design circuit boards. What I did was I changed the circuit so that I could utilize both halves of the IC, because it has twin outputs. It didn't make sense to use half of it, because I can use it as both a battery overcharge protection circuit and also a power output. Now I did have some idiosyncrasies with it. Some weird things were happening, because originally this part of the circuit was meant to be the power output ground. The way it works is I use the MOSFET. It's gate, drain and source. I use the MOSFET to ground the output, so that the output ground goes to the front panel sockets, and when the power is enabled, there's a ground present, so it enables the power to flow. But when the circuit cuts out, the ground is taken away basically, so the power is cut off. Now I had some weird things happening, because initially when I designed the circuit, it was in reverse, so I customized this part of the circuit with a PNP transistor, and the PNP transistor inverts everything. So normally when you get your output on, it actually turns the PNP positive negative transistor off, so the output is actually off when the chip is on. So my reset connectors, which are here, are reversed. So I thought, oh right, so my reset actually turns it off rather than turn it back on, which is no problem really, because I wanted to concentrate on protecting my cells, my battery cells, rather than reset it and enable the power and completely discharge the batteries. So I made quite a lot of changes to my resistor values, so you can see the resistor values in here in my circuit. I'll just zoom back out again, because that way if you want to copy my circuit you can do. Now that's the circuit diagram for my actual battery protection circuit. Obviously there's two outputs. There's a power switch ground and a charge switch ground, and you have to wire it so that you're utilising, so there's basically the solar power panel, the solar power energy comes in and is grounded by the switched ground, and the output of the battery is switched ground from the MOSFETs, right? But the actual circuit itself is always connected to the battery. This is the positive rail, this is the blue, the violet sort of sky blue. Is it green? Well, sort of in between blue and green. This is the positive rail, and the negative rail goes all the way around here. Oops. Right. That's the permanent ground, and the switch ground is up here. I could have these in different colour, I suppose. Now, most of the circuit, I made some changes to create an offset. I actually put the resistor, it's R8A. I put this resistor in here to create a bit of an offset swing, so that when the circuit's triggered, it doesn't oscillate and keep going on and off and on and off because of slight fluctuations in the voltage. So that way there's a bit of enough gap. For example, the voltage might be reactivated on the output when the voltage gets to say 13.8 volts, but for it to be actually cut off again, for the power to be disabled, the voltage has to drop to say about 8 volts or 9 volts. So if you get a massive short circuit or overload, it will cut the power off. So if the voltage drops to say about 8 volts, it cuts the power off. That's quite a big gap. So it doesn't come back on again until the voltage is charged to about 13.8 volts. But that's all adjusted by the trimmer anyway, so that can be anything really. But this offset is determined by this resistor here. The bigger the value, the bigger the less the offset, right? So if that's a 56,000 ohm resistor, 56k resistor there. Now if that resistor was 25k, then you would have a much bigger offset across the variable resistor here. Now, so the higher the resistor here, the lower the offset. Right, and as you can see from my other circuit, I had a different value there, 51k. Right, anyway, that's enough of the circuit diagram. Let's switch to, there's my actual board design, which it took me ages to do. Let's just turn off some of the layers. Just turn off the copper for a minute. Those are the component placements where I eventually put the component layout. This is my new board layout, by the way, not the old one. That's the component layout. Let's turn that off. Now, bottom copper, that's just the circuit board, the circuit tracks layout that I did. You'll notice the right at the top is backwards. That's because when you print it out and you have to transfer it to a PCB, it's mirrored, so it actually ends up the right way around once it's been transferred to the copper. Right, so that's there's a, let's see, bottom documentation, I'll forget that. I just made the pads bigger because some of the pads were a bit small, so I used some bottom documentation just to thicken the pads up a bit. It's not actually part of the circuit, but now let's see. Oh, that needs to go. Actually, I need to change that one. Let's see if I can highlight it. I'm having trouble here. Where is that one? Oh, I see, it's there. That wants to be actually. Let's see, turn it off a minute. Actually, I need to make that one. Let's look at error. I've just spotted an error. That's on bottom documentation. I need to make this one bottom of documentation. Let's change that one. Oh, it is bottom of documentation. Why is it a different colour? Well, that's strange. Oh, maybe because it was highlighted before. Right. Okay. Sorry about the confusion. Right. So put my bottom copper on. Put my top seal screen on. Top seal screen is the let's see, top documentation. Now that's the text for the descriptions of what things are. Reset charge. So it's just where I've added text later, just for more explanation. Put the circuit back on. You can see it's hard to read when you got this up, but it's actually printed on the top of the board, so when the copper is turned off, there's the top silk screen. You can see now where the writing belongs. So anyway, I just thought I'd make this video so I could just explain about my new design. This is my new design. It's much nicer. I'm going to make this one. I put both presets together in one place so it's easy to access. Now here's the, let's go on to, this is the voltage ladder I was talking about. As you can see, there's a voltage regulator there, volts in, plus 15 volts out, ground. Ground is connected to ground, obviously, and the way it works, it goes through my diodes. Now I'll just center this again. The voltage comes from the regulator, goes through a diode. Right, follow this track, and you get 13.3 volts out there, 13.4 volts there, 12.9 volts there, 13 point, I can't see, my eyes are terrible, zoom in, 13.6 volt, 12.9 volt, 12.2 volt, 11.5 volt, let's zoom out again, my eyes are really bad. And the voltage ladder, basically each diode is in series with the next diode, in series with the next diode, and there's a tapping from each diode on the ladder. This is what creates the ladder. So I'm showing you the circuit diagram for it actually now, and very simple. Ignore the layout of that, it's not very tidy. But these diodes are the outputs, so it takes all of the voltage from all the batteries into one, like I was showing in the earlier video, and all of the outputs come out here. This is the output, and that's ground. I'll just put that in for the circuit. Now, voltage ladder, let's see, where are we? There's the voltage ladder circuit board. Now let's do the 3D. Now I get a 3D representation of it now, you can see there. This is my 3D representation on my voltage ladder. Let's move it across a bit, because I know the picture, these are representative diodes, you know, so you can just get an idea. There's the regulator here, the big chunky thing there, and there's a copper circuit beside there. Let's get this right way up. It's reversed there. Now I'll just move this across, zoom out a bit. Now that's my actual, that's a 3D representation of my voltage ladder board, the one you saw in the battery box. Right, okay. Now let's get rid of that. And we're going to go to a 3D representation of my new circuit board. Here we go. Let's look at the 3D of that, what the new one's going to look like. There we go. That's what the new board will be like when I make it. This is a 3D virtual. We can pan around. This is the new one when I eventually get around to making that one. I'll just move across a bit and down a bit so we can get it in the video properly. And that's the back of the IC there. Whoops. As you can see, it's pin numbers 1 to 4, 5, 6, 7, 8. This is the back of the board. That's the back of the reset socket there, look, reset, and resets the power. Zoom in a bit more so you can see it better, because I don't know what resolution's like going to be like on YouTube. There's my reset charge socket. That's a representation of the power CMOS, but it's not going to be mounted on the board. It's actually going to be mounted on a heatsink with the wires coming off the board to the power MOSFET. But it's difficult to describe things in a virtual 3D thing, so right, let's just pan up the board. This is a virtual representation, as I say. This is my new layout. I've got to build this one next. I'll zoom out again. Hard to see. Let's just recenter it. There we go. So anyway, that's just some explanations. Because I made a new design. I wanted, when I finished building the other one, I actually found out there's a few things I had to move around, so I had to make some modifications on the board, but no big deal. I've sorted them out and incorporated all the modifications onto the new one. So, right, okay. Well, I don't know if there's anything else I can show you really. But as I said, the circuit diagram is simple for that's the circuit diagram really. There's just diodes and a regulator, and you can see where everything goes. These are placeholders. These are the yellow diode representations are where the diodes are. And you've seen the 3D model of that, and that's the representations of where the components are laid out on my actual circuit board for the power cutout protection circuit, and that's the circuit for the voltage ladder. There's not really much to it. It's quite simple. Anyway, enough of that. I better stop recording now. Get my pause button and stop it. Oh god, we were going for nearly 40 minutes. I hope that was informative. Bye bye. Come on, stupid thing. Ah, there we go. Full screen so I can see it. Right. I've set the voltage up on the laptop charge socket back up to 19 volts. So, right now when I plug this in to charge the laptop, which is down there, we should get full charge now instead of it pulsing, because yesterday I was just doing a pulse. Now plug it in. What's the current in amps? It's initialized. Right, it's charging at 3.5859 amps right now. The voltage is stabilized, so actually delivering to the laptop, which is under all this lot. Can't get to it because it doesn't work anyway. At least it wasn't. Now, so we're getting a good charge. Let me just get my meter out of the way because it's cluttering everything up. Oops. You know, this lead often falls off when I don't want it to, and when I want it to, it won't fall off. Right. I'm just gonna try and get to my try to get to my daughter's old laptop. It's the graphics chip's gone on it. The video chip completely fried. Aces are not very good. Now what's going on here? Right, I'll try and open the lid. I can never do this. Oh, I can never do it. Right. I can never get it off. Right. I'll try starting it up and see if anything happens. Oh, there's a big surge. Oh, look at that. It's from my trip, look. It cut my power off. There was a big psh. Did you hear that? Laptop stuff. Well, look at that. My cutout worked. I'll unplug the laptop. Oh, there we go. It come back on again. So overload protection works. Plug it back in again. Oh, it was using. Let's see what the amps are. Oh, it's cut it off again. The trip at the back has popped up, look. There we go. There we go, it's 4.39 amps. That's going to be a bit high, that, because it's going to throw that trip at the back again. See that trip? That'll pop up in a minute. Oh, it's protecting itself, so there's no overloads. Definitely works. Right, it's popped up again. See that little trip at the back? Unplug the front laptop thing. Push this down. That's it. Back on. See, the circuit works. It protects it from overloads. And the laptop is dead. It's lit up there, look, the power. But the screen is completely blank, nothing. So I'll just turn that off. Right, that's gone. So now I'm plugging the laptop back in again to charge. I was just to say, I'm only doing this as a test. Maybe we can get this fixed someday, or I can get my hands on a netbook. Now, let's see the charging again. There we go, 3.48 amps. It cuts out above 4 amps, so if there's a short circuit or anything like that, to protect the batteries, it cuts the power off. So yeah, there we go, it's taking out 3.46 amps at the moment, which is 39.2 watts. Well, now I'll explain the P properly, because there's a key at the front. I don't know if you can see that. It's in Chinese. Right, that's the reason why. It's in Chinese. I'm just going to try and get some light on that. Right. You'll notice that there's a key. It says, let me get this stable. U is V for volts, P is for watts, A is amps, C is amp hours, and H is hours. So you see it's got a Chinese symbol at the front. It's hard to read, and I'll just put my light back down again. Oh, sorry, my hands. I use the YouTube little built-in video steadier. I'll probably engage that again to keep it more stable. So right, we're taking quite a bit of power out at the moment. So the cutout works. Now I can probably push the reset button now, and you'll see it should cut out. Protect the charging off. Oh no, it came back on again. Look, press cut out. Oh, there we go. It went off and came back on again. So it works. Well, I'll unplug this. There we go, drop down to 120 milliamps. Let it build back up again. Put it back on watts. I like the watts because you get a high number. It's easy to monitor. And my little LED is set very dim actually, so it doesn't use a lot of power. It's actually wired into the voltage doubler inside. There. I know I didn't show you a lot yesterday, and there's my output sockets there. The output sockets go through the power switch, but the socket for the laptop is direct. I've still got some little tweaks to make I want to do later. As you know, my circuit board's right at the back there. It's under that copper shield thing. And my wires are tangled up, so I'm going to pull the lead out in a minute if I'm not careful. My circuit board's at the back there. And I'll put a new preset trimmer in there, which is multi-tone. It's a lot easier to adjust the voltage settings on that. So, right, I'm just going to put the lid on and stop the video for a minute. I think that's it actually, really.